Let's put our freshly developed postulate of measurement to use. One very helpful first step for deriving the tunnel effect is to first solve the one-dimensional Schrödinger equation for a constant potential energy V. This is very similar to the particle in the box. This time we guess a solution in terms of exponential functions, because this will suit our needs later on. If we plug this in the equation, we find that k has to be the square root of 2m(e minus v) over h bar. This last line basically says that the total energy is given by the sum of potential and kinetic energy. It also tells us what value k needs to have. This solution has a downside: it cannot be normalized. We could remedy this by either creating a superposition of infinitely many solutions of this kind, or by saying that our space is confined, but both would give us complications that, in the end, do not change the message. So for now, let's just act as if the solution was normalized and keep working with it. The solution is an eigenvector to the momentum operator with eigenvalue h bar k, so we can interpret it as a particle that is somewhere in space and is moving to the right in case of the plus solution and to the left in case of minus. Now we look at the situation that our particle encounters an obstacle. The potential in our situation is given by 0 if the position x is below 0, some value omega for obstacle if it is between 0 and some length l, and again 0 beyond that barrier. We can now write down the wave function. The solution for the Schrödinger equation that we found will work in each domain. Since the total energy E of the system is conserved in this setup, we will boldly ignore that part of psi to simplify the expression a bit. Left of the obstacle, we assume that a particle is coming towards it, and that some portion of it is reflected, as quantized by the prefactor r. We don't yet really know what's happening inside the domain of the obstacle, so it will just get a general superposition of a particle going left and right. Behind the obstacle, some portion quantized by the prefactor t might still be found going away from it. If you remember the particle in a box, you know that we have to see to it that our wave function and its derivative are continuous at positions 0 and L. This gives us 4 conditions. This system of 4 linear equations in 4 variables can be solved either by a series of arithmetic operations or, if you're like me, by writing the set of equations as a matrix equation and multiplying it with the inverse of the matrix. We find some admittedly lengthy expressions for the coefficients r and t. The probabilities for finding the particle in the particular state of either going in the opposite direction after being reflected by the obstacle or having passed the obstacle are, as you remember, given by the absolute squared of the coefficients. I don't really feel like evaluating these expressions explicitly, so I'll just make the simplifying assumptions that the square difference between the two values of k is much less important than their product, so I will ignore the former if the latter is added to it. Plugging this into the expressions simplifies them significantly. A classical particle will behave Boolean when it encounters an obstacle. Either its kinetic energy is larger than the potential energy, then it just climbs over it, or its energy is lower, then it will be reflected. A quantum particle behaves slightly differently. Remember the definition of k omega. If the energy is larger than the obstacle height, then it is a real number. If it is lower, then it becomes imaginary. With this in mind, let's go back to the simplified expressions of the probabilities. If a classical particle would overcome the obstacle, a quantum particle has a non-vanishing chance of being reflected anyway. The expression for the transition probabilities gives 1 here, but this is just an artifact of the simplification. The tunnel effect happens when the energy is lower than the potential energy needed, so if k omega is imaginary. A classical particle would get reflected, but a quantum particle has a rest chance of getting through. This probability is exponentially damped with the energy difference and the width of the obstacle, but it never truly becomes 0. I feel I should stress this again. This is a weird result. It is as if the particle just quickly borrows the energy to pass the obstacle it should not be allowed to pass. As it turns out, this is one valid interpretation. But more on that in another video. Until then, enjoy life if you can, and don't be ashamed if you can't.